All right, here we're going to find the input and output resistance of a MOS amplifier. Now the procedure is the same for any amplifier we look at. So we're going to start with the input resistance. When we're finding our input resistance, we're going to put a test voltage source, V sub x, at the input node, and we're going to measure the current that flows into the input when the output is open circuited. So here I've drawn the same small signal model for the circuit that we were looking at previously, noting that we're going to leave the output node open circuited, and we're going to put a test voltage source, V sub x. We're going to measure the current I sub x that flows from that test voltage source. Now, in order to make this calculation a little bit simpler, we're going to virtually remove R sub s from the circuit. And we note that at the end, whatever we find for our impedance V sub x over I sub x is going to be in parallel with R sub s after our calculation. So we're going to note a couple of things, that G sub 0 is equal to 1 over R sub 0, and I'm going to make a substitution called G sub d that's equal to 1 over R sub d. We're going to go ahead and write a KCL expression at the test voltage source. So we can say Ix is equal to Vx minus Vd times G sub 0 minus Gm times VGS. Of course, we note that Vg is equal to 0 since it's grounded, and Vs is equal to Vx. We can do a little bit of rearranging here and show that Vx times Gm plus Go minus Vd times Go is equal to Ix. Now, we can also go back up and write a KCL expression at the drain node, Vd. So if we wrote a KCL expression at the drain node, solved for Vd, and substituted it into this expression, we could then find an expression for Vx over Ix, and this would just involve a bit of algebra. You can show that this is ultimately going to be equal to G0 or Go plus Gd divided by Gd times Go plus Gm. Now, generally we can make a couple of assumptions. If Go is much, much less than Gd, in other words, the intrinsic conductance, output conductance of the transistor is less than the conductance of the load resistor, which is normally going to be the case, then we can make an approximation and say that this is equal to 1 over Go plus Gm. Now, we further normally can say Go is much, much smaller than Gm. In other words, we can say that Vx over Ix is approximately equal to 1 over Gm, if those two assumptions hold. Now, last thing here, because we removed Rs virtually at the beginning, whatever we find here is in parallel with Rs. Okay, when we're going to find the output resistance, again, we're going to put a test voltage source at the output port, and we're going to measure the current that flows from that source when the input port is short-circuited. Our input port in this case was the source, So we're going to ground the source, and we're going to put our test voltage source into the output, which was the drain. And we would measure Ix flowing through it. Now you'll note that both the gate and the source are grounded. So our gate to source potential is 0, which means that the dependent current source goes to 0. And if we go to find an expression for this, we'd ultimately show that R out is equal to R sub 0 in parallel with D. Now, as we said before, RO is normally much, much larger than RD, and so we can approximate this and say that R out is approximately equal to RD. All right, with that, we'll go ahead and stop talking about MOS amplifier analysis. In the next lecture, we're going to try and make some observations about the types of amplifiers and the fact that they almost always have a very similar, or I should say always have a very similar expression for their voltage gain in terms of the external resistances and the small signal parameters of the circuit. And so we hope to be able to just inspect the circuit and evaluate the gain without having to do a full analysis like this. So we'll do that in the next lecture and talk to you then.